Well, now our discussion is on the magnetic effect of current. Normally, magnetic effect means that we consider a conductor or a wire and then we pass current in that wire. And if we bring magnetic needle near that wire, we find that magnetism is generated. So this is what the aim of the topic to explain how the current will generate magnetic field and how the magnitude of current affects the magnitude of magnetic field. Now, first of all, our discussion is on force on a current carrying conductor due to magnetic field. Wherever we use the term magnetic field, we are indirectly referring to magnetic induction. Its unit will be Tesla or Weber per meter square, or it will be Gauss. And one Gauss can be taken as 10 to the power minus 4 Tesla, and 1 Tesla or 1 Weber per meter square, that will be taken as 10 to the power 4 Gauss. Now, first part is, if current I is passed through conductor of length L and it is placed in magnetic field B, then force acting on it will be F is equal to IBL sine theta, or F is equal to I into the cross product of L and B. If theta is 0, that is B is parallel to L, then F is equal to minimum. This can be seen in the diagram. The length of the conductor is shown as L, the current passing is I, and angle theta is the angle made by the wire or the conductor with direction of magnetic field. If theta is 90 degrees, that is B is perpendicular to L, then F is equal to BIL, and that is maximum value of the force. The direction of magnetic force is perpendicular to the plane of L and B. According to right-hand screw rule, following two rules are used in determining the direction of magnetic field. The first is right-hand palm rule. If the right hand and the palm are stretched such that thumb points in the direction of current and the stretched fingers in the direction of magnetic field, then the force on conductor will be perpendicular to the palm in the outward direction. And then comes the Fleming's left hand rule. If the thumb, the forefinger, the central finger of the left hand are stretched such that first finger points in the direction of magnetic field and the central finger in the direction of current, then the thumb will point in the direction of force acting on the conductor. Now there are certain examples solved based on the force on current carrying conductor. The first example is the distance between the wires of electric mains is 12 centimeters. These wires experience 4 mg weight per unit length. The value of current flowing in each wire will be. Now, before solving the question, you must understand that mg weight is a smaller unit of force in gravitational system. Basically, the gravitational unit of force are always expressed in gram weight, kilogram weight, milligram weight. You will further remember that 1 gram weight is equivalent to 980 dynes and 1 kilogram weight is equivalent to 9.8 newtons. So you can make the calculations for 4 mg weight, where 1 gram is equivalent to 1000 mg. Now, solution to the question is that force over length is mu naught I square over 2 pi d. Compute the values and calculate the square root of these numbers. That will come to be 4.85 amperes. And another example, in the adjoining figure, the force on current carrying loop ABCD due to long current carrying wire will be. Now current is I1 and the current in the loop is I2. Face AB is close to a conductor carrying current I1 and the side of the square that is taken as A. So what exactly we are finding? The repulsive force on the side AB of the loop. Why repulsive force? Because currents are in opposite direction. Current I1 is F1 equals to mu naught I1 I2 L divided by 2 pi R. Now given mu naught over 2 pi equals to 2 into 10 to the power minus 7 newtons per ampere square. I1 is 20 ampere, I2 is 16 ampere, R and D both are equal to 4 centimeter converted to meter. L or A are the same thing, that is 15 centimeters converted to meters. B is 6 centimeters converted to meters, and compute in the equation F1 equal to mu naught I1 I2 L over 2 pi R. And our conclusion is that F1 will be equal to 2.40 into 10 to the power minus 4 newtons. This force will act away from the current carrying wire. Similarly, the attractive force on the side CD of the loop due to current I1 is now R is equal to D plus B. All the numbers are to be converted to MKS system, compute in the equation, and force F2 will be calculated, which is found to be 0.96 into 10 to the power minus 4 newtons. This force will act away from the current carrying wire. The force on the sides AD and BC of the loop will be equal and acting downward and upward respectively. Hence, they will neutralize each other. Net force on the loop is F1 minus F2. After computing the values, the number comes to be 1.44 into 10 to the power minus 4 newtons. This force is acting away from the current carrying wire. You can see the figure. Now, magnetic force between two current carrying parallel conductors. Normally, the rule is that whenever two parallel conductors carry current in same direction, they attract, and in the opposite direction, if the current is flowing, they will repel. Now, this is more elaborately indicated like this. In the figure, two parallel conductors are shown. The distance between them is D. Let I1 and I2 be the currents flowing in these conductors. When current flowing in these conductors are in the same direction, they attract each other. When currents flowing in them are in the opposite direction, they repel. The force of attraction or repulsion acting on unit length of each conductor is given by function F is equal to mu naught over 2 pi I1 I2 divided by D newtons per meter. D is the distance between the two parallel wires. Force acting on conductor of length L, that is F dash, this is equal to FL mu naught I1 I2 into L over 2 pi D newtons. Attractive or repulsive force, that is modulus of force on first with respect to 2 equal to force on second with respect to 1. So magnitude will be F12 equal to minus F21. They are equal in magnitude but opposite in direction, as shown in the figure, where F12 is the force on the conductor 1 due to conductor 2 and F21 is the force on second due to first conductor. Now we come towards the definition of ampere. If I1 equals to I2, that is equal to 1 ampere, and D is equal to 1 meter, that is the distance between the two parallel wires, then F is mu naught over 2 pi, 4 pi into 10 to the power minus 7 over 2 pi. 4 pi 10 to the power minus 7 is the numerical value of mu naught, and it is divided by 2 pi. The value comes to be 2 into 10 to the power minus 7 newtons per meter length. So this is basically the definition of ampere. If two conductors of finite length and negligible cross-sectional area are placed parallel to each other at a distance 1 meter apart, each carrying same current in the same direction, produce a force of attraction of 2 into 10 to the power minus 7 Newton per meter between them, then the current flowing in each wire will be 1 ampere. You can check up the figure. If the currents are in the same direction, attraction will take place. D is the distance between the two parallel wires. Now, from above definition of ampere, the new unit of mu naught is 2 into 10 to the power minus 7 Newton per meter equals to mu naught over 2 pi 1 ampere square divided by 1 meter. The value of mu naught is 4 pi 10 to the power minus 7 newtons per ampere square, and dimensions of mu naught, that is given as mlt minus 2 over a2, that is equal to mlt minus 2a2. Well, in this context, you will further remember that absolute permeability, that is mu naught, can also be expressed as Weber per ampere meter, or it can be Henry per meter. And if we wanted to establish the dimension of mu naught, we can take one function, that is mu is equal to mu naught multiplied mu r. Mu r is the relative permeability, mu naught is the absolute permeability, and mu is the permeability of the medium. Two parallel wires are placed one over the other. One wire is stationary, other is free. If free wire is above the stationary wire, then in order to stop the free wire, falling currents will have to be passed the two wires in opposite direction. The force of repulsion due to them will balance the weight of the free wire. If free wire is below the stationary wire, then currents will have to be passed in same direction. In this case, the force of attraction due to them will balance the weight of free wire. Now, the sixth point is that some weight is suspended from spring. If current is passed through it, then there will be attraction between the turns due to flow of current in turns in same direction, and spring will contract. Now, next example is that two parallel wires are situated at distance 10 centimeters. If 1 ampere current is flowing through each wire, then calculate the force per unit length on any one of them. So, what we are finding, that is, as given in the figure, we are finding X, Y, Z are three currents carrying wires. What will be the direction of resultant magnetic force? There will be attraction between X and Y and repulsion between X and Z. Because in X and Z, the currents are in opposite direction, wherein X and Y, the currents are in the same direction. When currents are in the same direction, the wires have tendency to attract, and whenever the currents in opposite direction, the tendency is to repel. The resultant force or the total force will be Fyx plus Fyz. By computing the values, we come to this function, mu naught Ix into Iy over 2 pi r1 plus mu naught Iy into Iz divided by 2 pi r2.